Hello, my name is Evgeny Shapiro. I'm a senior product manager responsible for fluids products at Rotary Simulation, and today I'm delighted to present new features in WAVE and WAVE-RT in our first release of 2024. WAVE and WAVE-RT provide high-fidelity modeling capability for internal combustion engine development. With WAVE product suite, our customers can accelerate virtual product development and leverage the latest innovation and R&D in 1D and real-time CFD space. Realis products deliver a personalized experience while minimizing development costs and placing our customers at the center of decision-making. Today, we will discuss new and exciting features in the 2024.1 release and provide an overview of how these features can help you create accurate models and streamline your CE analysis workflow. 2024.1 release, which went out on the 20th of March, is packed with new features addressing new simulation challenges. The core theme of the release is our commitment to improvement of the accuracy, usability, and speed of 1D and real-time CFD analysis. In new applications and functionality category, we improved substantially predictive combustion modeling for biofuels in diesel applications, delivering precision for your simulations. Additionally, we have introduced new options allowing real-time simulation of rotary engines, bringing our market-leading real-time solar capability to our customers working on UAV development. This release also features a number of user experience enhancements, mainly focusing on complex models with a large number of model elements and a large number of simulation cases. Our GUIs for preprocessing and model building now boast improved speed, stability, and responsiveness, ensuring a smoother experience. Navigating complex models has been made much easier with several new features added, allowing flexible canvas navigation. We have made it easier also to work with large simulation case sets with a number of case table enhancements. We have also enhanced substantially the stability of working with parameterized geometrical models in the WAVE-Build 3D preprocessor. Focusing on simplifying and accelerating workflows, we have introduced new features which improve meshing and component preparation in WAVE-Build 3D. Also, it's now possible to remesh WAVE-Build 3D components directly from WAVE-RT's GUI. Finally, we are proud to announce support for the SpeedGoat hardware-in-the-loop platform, expanding options for real-time simulation which are available to our customers. Let's delve deeper into a selection of these features. And if you have any questions or would like to explore how Realis products can optimize your modeling workflow, don't hesitate to reach out to us at support@realissimulation.com. Let us start with the combustion, the core of predictive engine modeling capability. Biofuels and drop-in renewable replacements for conventional diesel can be an eco-friendly and efficient alternative for internal combustion engines in heavy-duty and power generation applications. In 2024.1, our new features include extending our predictive diesel combustion model to accommodate any fuel type. Additionally, we have introduced new kinetics modeling capabilities that enable the simulation of complex diesel alternatives in both WAVE and WAVE-RT, helping our customers explore sustainable energy solutions. In 2024.1, the original diesel predictive formulation by Barber was expanded to incorporate fuel-specific premixed mode flame speed. The flame speed can be specified as a Met-Galchenyuk type correlation or as a table mapping pressure, temperature, EGR, and equivalence ratio to the auto-ignition delay time. The flame speed tables for specific fuels can be built using Combustion Toolbox, Realis Simulation's Swiss Army knife of kinetics tools, leveraging the power of Camterra. Note that for users who prefer the correlation approach, the toolbox also provides utilities to construct the parameters of Met-Galchenyuk correlations from detailed kinetics tables. Flame speed tables for diesel surrogates and hydrogenated vegetable oil are provided in the installation. To facilitate correct calculation of auto-ignition for any diesel-like fuel, we have developed a new auto-ignition model, providing auto-ignition delay directly from tabulated kinetics using a spray plume sweeping approach. 2024.1 installation includes auto-ignition delay tables constructed with this novel method for European IDEA diesel and hydrogenated vegetable oil surrogates. Users can create these new auto-ignition tables for any required fuel composition with Realis Flame tool. The new models are available for both WAVE and faster than real-time WAVE-RT applications. The resulting combination of improvements and delivered pre-computed tables allows our customers to easily explore the effects of drop-in biodiesel replacements on performance and emission of their powertrains. The example shows drop-in replacement of hydrogenated vegetable oil instead of diesel, conventional diesel, in a 640-liter 18-cylinder twin-turbo genset. The genset is running with controlled VMEP. The replacement of the fuel is as simple as selecting the correct fuel from the material database supplied, specifying the auto-ignition table supplied in the installation, and in the predictive combustion model, switching to laminar flame speed provided in the installation for the surrogate of hydrogenated vegetable oil. In this case, it's endodecane. The resulting simulation shows that the expected benefits of using HVO instead of conventional diesel are realized. So the torque is controlled, which means that the BSFC goes down, fuel mass flow goes down, and NOx output goes down. The cumulative functionality delivers accurate 1D CFD models, correctly reflecting the effects of the composition for complex biodiesels. Continuing the theme of improving modeling of spray-driven combustion processes, in 2024.1 we have added a new method of accurately specifying injection profile for complex injection strategies. The new injection model allows users to input the measured data as injection mass flow rate profile for each energizing time and rail pressure. WAVE and WAVE-RT will then recalculate the supplied data so that the users can drive the injection by actuating injected mass and pressure. The resulting functionality improves the modeling of spray-driven combustion for design and virtual calibration applications. The data conversion process also generates a number of useful inverse maps, showing the dependency of normalized flow rate on rail pressure and energizing time, injection delay, and injection duration on rail pressure and injected mass, and the minimum injected mass as measured on rail pressure. The image on the left shows the edit panel for the new injection rate and the visualization of an injecting profile at a particular rail pressure and energizing time. By enabling precise control of the fuel delivery, this feature significantly enhances the accuracy of combustion simulations, ensuring more reliable and realistic results for complex engine configurations. Rotary engines play an important role in UAV applications due to their efficiency and compact design. WAVE offers robust and precise methods for modeling rotary engines using a straightforward three-chamber analogy. In this release, we have extended the modeling of rotary engine to enable it in our faster than real-time solver WAVE-RT. The key improvement which unlocks this faster than real-time modeling is the support of imposed piston motion and piston motion actuation in real time. Furthermore, we have also included the support for stratification in the predictive SI combustion model, which makes it possible to reflect the effects of changes in mixing on the properties of the combustion in direct injection applications. This functionality is not limited to UAVs, it's also applicable to other market sectors, for example, to direct injection gasoline. The example here shows how the wave canvas model looks for such a rotary engine application for a single rotor configured for export to WAVE-RT and also for running WAVE-RT in line with desktop model in RDesk. The model can be run in RDesk or the model can be exported and run in Simulink for software envelope applications, for model envelope applications, deployed on Hill, and as we can see here, the typical real-time multiplier of such a model is below 0.1. So model runs faster than real-time by a factor of more than 10. Our next new feature concerns development of finely tuned exhaust systems. This is a multifaceted challenge which demands precise computational measures to accurately capture, analyze, and enhance acoustic performance. And in our 2024.1 release, We have implemented several enhancements in our geometry preprocessing tool WaveBuild 3D and its integration with the WAVE-RT GUI. The first of these is the new functionality that allows precise positioning of baffles within the exhaust system. Users can now specify the coordinates directly or link the position to control points available in the geometry, which provides enhanced control over the arrangement of baffles. This functionality, when combined with support for zero-thickness baffles, which is another new feature in 2024.1, enables precise alignment of the 3D mesh for accurate discretization. In this example, we precisely position a baffle by using our new 3 points option. The 3 points can be picked up directly from the underlying geometry using control points. Now, once the baffle has been positioned correctly to reflect the symmetry of the geometry, we can change its thickness to 0, and with the 0 thickness, the baffle will be used only for guided mesh partitioning. The 3 points can also be specified by direct input of the coordinate. And once we have created the computational mesh, we can see that the Y junctions are aligned, guided by the position of the baffle, and the mesh reflects the symmetry of the geometry. With this finer control over baffle placement and alignment, users can achieve greater accuracy and reliability in their simulations, which ultimately leads to better designs. Modern muffler designs can incorporate exhaust valves to regulate the flow of exhaust gas, controlling both noise and back pressure levels. Typically, these valves are represented as orifices or within the WaveBuild 3D component. Adding an actuator to control such valves in previous versions of Wave required merging the component on the canvas in WaveRT GUI, that is, replacing the actual component with the mesh of the component. From this release, WaveBuild 3D offers users the ability to directly specify orifice actuation when editing the geometry. This simplifies the process of integrating a generic valve into a 3D component. The feature allows the users then to control the valve directly from the WaveRT GUI without the need to merge the component, which simplifies the overall workflow. In this example, we are picking up an orifice for an illustration, and we can specify that this orifice is actuated. Then we mesh the component and save the component, after which it will be updated on our desk canvas. We can see that there is an actuator appearing in the component, and we can use control elements such as, for example, source, to connect this actuator and set its value, for example, by using parameters by specifying orifice diameter parameter. This new feature allows users to work with 3D geometries with actuated orifices while preserving the information about the actual 3D source geometry in the model. It also can speed up the simulation setup, as we do not have to import the mesh of the component into the model. Our next feature is aimed at speeding up the simulation setup. Modern engine models can have a large number of elements. However, navigating through these elements within complex models can often prove challenging, leading to delays in simulation setup and troubleshooting. 2024.1 release introduces new canvas navigation features Find and Zoom to. Find functionality, which is available through the toolbar or Ctrl+F keyboard shortcut, allows users to quickly locate named elements, simplifying the navigation process. The feature supports search by name using a part of a name or a regular expression. It then displays the list of found elements, and users can scroll through the list with the canvas focus following the selection. The Zoom to feature is available through the context menu of the element in the tree, as well as through the Edit panel. It allows users to focus the canvas automatically on the required element and its neighbors. Let's illustrate this functionality using our turbocharged gasoline direct injection engine as an example. The Find functionality can be accessed through the toolbar and also through the context menu of the canvas or by Ctrl+F shortcut. And it's mostly useful when dealing with complex geometries with many ducts and Y junctions. For example, in this case, we have a merged component in the intake side, and we can easily find junctions of this merged component and scroll through them with the canvas following our selection. The Zoom to functionality is mostly useful when we already have the element selected or we know its name, so we can see it in the tree, and we need to quickly find where it is on canvas. For example, we can look at this receive element and use Zoom to context menu to quickly zoom the canvas to the location of the element. We can also use the Zoom to button in the edit panel to quickly navigate to this sent element, for example. These new features streamline setup and troubleshooting of complex models. Moreover, by simplifying navigation and troubleshooting, these features save valuable time for CA teams, enhancing productivity and efficiency. 1D CFD simulations often involve complex parametric studies with variations in parameters defining combustion, injection, temperature, etc. across different engine operating points. However, managing the resulting complex tables, which can range from a few to thousands of cases, presents challenges in the form of potential input errors, which can lead to time-consuming troubleshooting. In this release, we introduce a parameter profile feature. This feature offers a visual representation of input parameter values by providing plots of parameter variation against the case number. Parameters profiles are available in the case table, so we can use this profile button to open the plot, and we can open the plot in horizontal or vertical layout. So let's try the vertical layout. They provide immediate visual feedback. So for example, in this case, if I plot fuel, I can immediately see that there is an issue with the fueling for case 12, which doesn't look right and indicates a potential input error. In addition, we can cross-plot parameters. So for example, I can cross-plot fuel against the burn duration by selecting multiple rows. Each parameter is plotted on its own y-axis if their units are different, and parameters with the same units are sharing the same axis. Other useful enhancements of the case table include ability to quickly resize all columns to contents, which is useful when you are dealing with the files and with path names in your parameters, and also the size of the columns, the width for the columns is now persistent. It's stored directly in the session file. Our last headline feature is the addition of a new platform to the list of hardware-in-the-loop platforms supported by WAVE-RT. WAVE-RT stands out for its exceptional accuracy and flexibility in virtual calibration. Here at Realis, we're committed to continually broadening our support for hardware-in-the-loop platforms to streamline virtual calibration workflow regardless of your hardware setup. In our latest release, we are thrilled to unveil support for powerful SpeedGoat hill platforms, delivering effortless hill deployment from the familiar MATLAB Simulink real-time environment. With the new 2024.1 release, deploying your faster-than-real-time engine models on SpeedGoat hill platform is a matter of 3 simple steps. We create the models in a simple and intuitive GUI, connect the models in MATLAB using WAVE-RT mask, and seamlessly deploy on SpeedGoat hill target using MATLAB Simulink real-time. In addition to the main features, this release contains a number of other new features, usability, and productivity enhancements. In our Desk Wave plugin, it is now possible to import parameters from a Wave Build 3D component and remesh it, applying the values of the parameters from the active case. This simplifies the process of analysis when the user varies the geometry by applying parameters. The image of the modified component is updated on canvas automatically, which provides visual feedback. There are a number of speed improvements for very large models, particularly when merging large components on canvas and upgrading wave models with large numbers of elements. In another enhancement, which improves the workflow for large models, the placement of actuators, which are generated by the interpolation map creator, has been improved. Now they appear to the left of the model as opposed to next to the actuated element, which makes the model canvas much easier to navigate. The last RDesk enhancement in the table aims at organizations managing central installations. The default preferences for all RDesk plugins are now stored explicitly in a preference file available in the installation tree. This makes it possible for that IT administrator to deploy default preferences easily for all users of Realis software tools in the organization. In WAVE-RT, we have added support for GMEP and PMEP sensors, air-to-fuel ratio summary variable, and actuation of injection pressure. We have also adjusted reported start of combustion for diesel predictive combustion model to handle correctly cases where pilot pulses are present, but the user is actuating them to have zero mass. Tools enhancements feature ability to set global preferences for cluster settings in RDesk Tuner, which allows users to set parameters of their queuing system globally for all sessions. Furthermore, it's now even easier to translate your models from GT to WAVE. We have enhanced the import from GT with a number of new features driven by the elements typically encountered in Rotary engines. Finally, the post-processing in RPost has been improved, allowing customers to change the source file in bulk with one operation on all selected curves, simplifying analysis of complex data sets. The full list of enhancements and corrections is available in the release notes provided in the manual. Thank you for your attention. We hope that our first release of 2024 will help you build accurate engine and powertrain component models faster and more efficiently. If you have any questions or would like to explore how Realis products can optimize your CE workflows further, don't hesitate to reach out to us at support@realis-simulation.com.